My name is Adnan, and today I'm going to explain part 1 of Lab E4. So, part 1 is the stepper motor controller. It has 3 inputs 1, 2, and 3. The first input is EN, enables stepping. Second input is CW, controls the direction of stepping. If it's 1, it's clockwise. If it's 0, it's anti-clockwise. And the third one is the clock. So, if the first input EN is 0, then it keeps on looping itself. If it's 1 and the second input is 1, then it's gonna go clockwise. If EN is 1 and CW is 0, then it's gonna be anti-clockwise. And this is stepping sequence timing diagram. And so if you look over here, this is state 0 and output 0. If it's output 0, then if it's clockwise, it's going to be S1. If it's anti-clockwise, it's going to be S3. And if you look at the state diagram, if it's clockwise, S0 will go to S1. If it's anti-clockwise, it will go to S3. And for S1 and output 1, if it's clockwise, it's going to go to S2. If it's anti-clockwise, it's going to go to S0. So if we look at the state diagram, if it's clockwise, it's going to go to S2. If it's anti-clockwise, it's going to go to S0. And for the third one, S state 2 and output 2, if it's clockwise, it's going to go to S3. If it's anti-clockwise, it's going to go to S1. In the state diagram, if it's going to be clockwise, then it's going to go to S2 to S3. If it's anti-clockwise, it's going to be S2 to S1. And the final one, state 3, output 3, if it's clockwise, then it's going to be S0. If it's anti-clockwise, it's going to be S2. Over here, if it's going to be clockwise, it's going to go from S3 to S0. If it's anti-clockwise, it's going to go from S3 to S2. So over here, these are the 4 states, and we've assigned these 4 states to this one. And then if you look at B and A, it's 0, and EN is 0. So no matter what the value of the CW is, if EN is 0, then it will keep on looping on both of them, over here and over here as well. And then for when EN is 1 and CW is 0, it's going to be anti-clockwise, which is S3. And if EN is 1 and CW is 1, it's going to be clockwise from S0. That is S1. And over here, S1. So if EN is 0 and CW is 0, it's going to keep on looping. That's why it's still S1. And it's the same for this. EN is 0 and CW is 1. So no matter what the value of CW is, if it's EN, then it's going to keep on looping. That's why it's still S1. And over here, EN is 1 and CW is 0, so it's going to go anti-clockwise. That's why S1 anti-clockwise to S0. And over here, EN is 1 and CW is 1, so it's going to be clockwise. That's why S1 to S2. And over here for S2, if EN is 0 and CW is 0, so it's no matter what the value of CW is, it's going to keep on looping if EN is 0. That's why it's still the same. And for the second one as well, it's still the same. So on and so forth. So this next state, the value of next state is according to the name which we got from the output. So over here we assigned S0 to the 00. That's why it's 00. And over here it's also 00. And over here we assigned this next state according to S3, and we assigned S3 to 11. That's why it's 11. For FF inputs, we take an example of S1 and S3 only. So if you look here, the present state for P is 0 and the next state is also 0. So according to the table, 0 is 0x. That's why it's 0x. And for S3 stable, if we take this, if the present state for A, it's 1, and the next state is 0 for A, so it's gonna be 1 0 is x1. That's why we got x1. And for the outputs over here, we look at the truth table for O0. So according to the truth table, O0 is going to be B0 A0, and that's why the binary is like this. And for state 1, it's 0010. So if you look at the truth table for this one, it's for O1 it's A0 B, and for the state 2, if you look at the truth table over here, state 2, according to this one, it's O2 is A B0, and for the state 3, if you look at the source table, it's O3 is AB. So this is the schematic for part 1 which we created. So over here we've used 74SC107, which is JK flip-flop, and over here it is 74SC08, which is the AND gate, and over here it's 74SC86, which is the XOR gate, and this is 74SC00, which is the NAND gate. And these are the truth table for that schematic. This is for JB, KB, JA, and KA. So for the part 1 schematic, now we're going to implement on the board. So I'm going to set the clock module to 1 Hz. So this is the EN and this is the CW. So if to make sure it's on loop, we make CW1. If you look over here, it's on loop. That's why it's still there. And if EN is 1, it's gonna start going anti-clockwise. If EN is 1 and CW is 0, if CW is also 1 and EN is also 1, it's gonna start going clockwise. And if EN is 0, it's gonna stay in the loop.
My name is Mohammed and I will explain part 2 in lab 4. So this is our state diagram. We got this state diagram from our truth table. This is the equation that we came up with in order to get the truth table. For the D flip-flop, the answer for the next state will depend on the D flip-flop. We determine that D3 is equal to X3, Q3 equal to X2, Q2 equal to X1, D2 equal to Q3, D1 equal to Q2. So we determine the first state is 100 based on the timing diagram. So this is 100. Therefore, the first present state will be 100. And we got D3, D2, D1, 010. D2 we got 1 because it depends on the XOR of X1, X0. So 00 we got D3 to be 0, D2 it depends on Q3, therefore Q3 is 1, therefore D2 is 1, and D1 is 0 because D1 depends on Q2, so Q2 is 0. So we got the next state to be 010. Now for the next state, it is for the next present state it will be 010, and then we check D3. D3 is equal to X3, therefore it will be the X3 is the X1 XOR X0. So X1 XOR X0. So 1 and 0, based on the truth table of XOR, we get 1. So D3 is equal to 1. And D2 is equal to Q3, therefore we get 0. And D1 is based on Q2, so Q2 is 1, therefore D1 is 1. So the next state will be 101, and so on and so forth. This is our schematic diagram for part 2A. We have X2 connected to the Q0 and X0 connected to Q1, X1 connected to Q2. So for our schematic diagram, we set pin 2 to be high based on the data sheet. If you can see from the data sheet here, pin 2 is actually DSP. So when we go down to the table, we check DSP is always set to high based on the data sheet. And the MR is connected to pin 9. So pin 9 here is always set to high as well based on the data sheet. And for CP is the clock, which is connected to pin 8 and is connected to the clock module. And pin 1 is connected to pin 6, which is XR. The same connection will be for part 2B as well. So now let's check the circuit diagram. the actual circuit for our schematic diagram. If we check the state diagram, we will see the combo 0, 0, 0 will keep looping forever in itself infinitely. And in order to break that loop, we change one of the XOR input to be 1 in the second XOR gate. So we change pin 4, which is connected to the ground, to be high. So we go to the circuit and we see that when we press the input for the 0, 0, 0 loop, it will keep looping in the 0, 0, 0 forever infinitely. So in order to change the loop into a new loop, which is 0, 1, 0 to 1, 0, 1, 1, 1, 0 to 1, 1, 1, 1, 1, 1 to 1 to 0, 1, 1, and 0, 1, 1 to 0, 0, 1, 0, 0, 1 to 1, 0, 0, and back to 0, 1, 0. And in order to change that, we change pin 4 and connect it to the switch module and set it as high. So we change input, then pin 4, and connect it to the switch module, and we set it as high. After setting the input to be high, we connected the pin 4 to the switch module and we switched it to high. Now we can see that the loop is going from 0, 1, 0. Let's start 0, 1, 0 to 1, 0, 1, 1, 0, 1 to 1, 1, 0, 1, 1, 1, then 0, 1, 1, 0, 0, 1, then 1, 0, 0, then back to 0, 1, 0. So again, it goes to 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, then back to 0, 1, 0. So that's it for my part. So now we will check the DSO reading in order to determine that the XO is following a random pattern or a sequence pattern. If it follows a sequence pattern, it should follow the XO, and we will determine that in the DSO reading now. So we checked the sequence of XO. We connected channel 2 to the output, which is X0, and we connected channel 1 to the clock module. So we check the sequence of X0. First it goes from 0, then it goes back to 1, then it goes to 0, then it goes for 3 phases to 1, and then it goes back to 0, and so on and so forth for the X0. So if we check the timing diagram, it is the same as DSO reading. So we determine that the sequence of XO is not random, but it follows the pattern of the state diagram. So that's it for my part. Thank you. So this is the 7-bit LFSR. We forced the 7-bit LFSR into a sequence which can produce a maximum state of 1 to 7. And the clock module is set to 500 kilohertz to determine the waveform. Now we can see the waveform in the DSO reading. So the part 2B, it asked us to change 2 wires in order to come up with the 7-bit LFSR with a sequence of length 127. This circuit is constructed by changing part 2A, and we changed the XO, which is connected to pin 4, to X3, which is connected to pin 6, and we changed the X1, which is connected to pin 5, and we connected it to pin 12 in Q6, and instead of X1 it's X0. So the question asked us if it shows a random sequence. So if we run and stop the oscilloscope, we see that it shows a random sequence. So it's not following the sequence of XO, which is in the part 2A. This means it follows a random sequence. So that's it from my part. So I'll be explaining part 3 in lab 4. So this is the part 3, which asked us to design a Mealy state machine to detect the sequence 011. The reason we are detecting 011 is because we looked at it from left to right. So we used the part 2B circuit as a PRBS input to test the circuit. So this is the state diagram that we came up with, and if it is 0, 0, it will go to F0, and if it is 1, then it will go back to idle and it will loop in itself. And if it is 1, 0, then it will go to F01, and if it's 0 0 it will keep looping in F0. And this one, if it is 0 0, which is mean the input is 0 and the output is 0, it will go back to F0. And if it is input is 1 and the output, we got it and we got the desired output, then we go back to idle. So this is the table that we came up with, and we assigned the idle to 0 0, we assigned F0 to 0 1, we assigned F01 to 1 0, and this is the don't care, and we assigned it to 1 1. So we have the input 0 1 0 1 0 1 and don't care for the part that we didn't assign anything for. So we determine that if it is 0 0 it goes to F0, therefore the name is F0, and if it is 1 then it will go back to idle, and if the input here for F0 is 0 then it will go back to F0, and if the input is 1 then it will go to F01, and so on and so forth for the rest of the inputs. So this is the AB. 01 represents F0, 00 represents idle, 01 represents F0, 10 represents F01, and don't care represents the don't care. So this is the truth table that we came up with for the input of our part 3 circuit. So DA is equal to B and W, but we used De Moivre's theorem and we got B naught plus W naught, which is the NOR gate, and DB is W naught, and F is equal to A and B, and A and W, and we use De Moivre's theorem to get A naught plus W naught. So this is our circuit schematic diagram for part 3, and we connected from part 2B, which is this input. We connected 12, which is X naught, which is the sequence that we want to read. We connected it to W, which is pin 1 and pin 2. So now this is our circuit that we designed. We are using 164 and 86, which represents part 2B circuit, and we are using 74 and 00 and 02 for part 3 circuit. So this is our DSO reading that we came up with, which detects the 011 sequence. So if we look here, it is 0, then it comes to 1, then 1, so it detects 1. So then 0 1 1, so it detects 1. Then 0 1 1, it detects 1. 0 1 1, it detects 1, and so on and so forth for the rest of the sequences. So that's it for my part. Thank you.